So when we're talking about infinite limits and limits at infinity, there's some things about polynomials and rationals that you need to remember. Because basically the two functions that we're talking about almost always are either polynomial functions or they are rational functions. So for polynomials, we're talking about n behaviors. What is going on the graph as x approaches positive infinity to the right or negative infinity to the left? Okay, and hopefully you know there are only two types of polynomials, even polynomials and odd polynomials. And each of these evens and odds have positives and negatives. Okay, and they each have their own n behaviors depending on whether we're going to the left or whether we're going to the right. Okay, so for even positive polynomials like x squared and x to the fourth, those are always opening up. So for the n behaviors of polynomials, the limits, right, the limits at infinity for either one of these are always going to be positive infinity because the ends of these graphs are always going up. As you square or as you raise something to the fourth power, you get very large positive numbers. Okay, now if we're doing it for the negatives, right, a negative one, those open down. The n behaviors of negatives are opening down, so you're going to get negative infinity as the limits, whether you're going to the right or to the left. So for even polynomials, those open up and go to infinity, and for odd polynomials, those open down and go to negative infinity. Okay, but what about our odd polynomials? Hopefully you know all even, or rather positive odd polynomials, okay, experience growth like this. Okay, this might happen to be a cubic one. So to the left, as x goes to negative infinity, so do the y values, that's their limit. And on the right, as x goes to positive infinity, the limits of these also go to positive infinity. So for positive odd polynomials, the limit is the same as the x values. For the negative odd polynomials, those have a sketch that looks like this, and their limits are opposite of your x's. So as x goes to negative infinity, the limit is positive infinity, and as x goes to positive infinity, the limits are negative. Okay, so those are the n behaviors of your polynomials. You either have even positive and negatives or odd positive and negatives. So those limits should be pretty soon because they talk about the n behaviors. Now, how about for our rational functions? Okay, for your rational functions, those always have some type of an asymptote, right? Like 1 over x is in the positive first quadrant and in the third quadrant. So that's the graph of 1 over x. So as x goes to positive infinity, the y values are going to the horizontal asymptote. Okay, and if you don't have any vertical shifting, then that horizontal asymptote is 0. Okay, the x-axis. Same thing as if it goes off to the left, to negative infinity. The limit is also the horizontal asymptote, which in this case for 1 over x happens to be 0. Okay, so if we can take the limit of 1 over x, then that answer is 0. But what about if we had 1 over x squared? Okay, for that one, well, that's just a volcano-looking graph because now we've made all of the y values positive. And as x goes to infinities, well, the limit is still going to the horizontal asymptote. Okay, in this case, both of these are 0 also. So if your rational function doesn't have a vertical shift, then the answer to the limit as x approaches infinities are zeros. Okay, and that's going to come in pretty handy when we start using the limit analysis of these type of rational functions. So one more mention for rational functions. There's 3 different types. There are functions that are always going to be bottom heavy. Okay, and what that means is the power of the denominator is greater than the power of the numerator. Okay? Like in this example, you have an x cubed in the denominator and an x in the numerator. Well, hopefully you know that the horizontal asymptote is going to be the x-axis. Okay, y equals 0, and we'll show that using calculus here in a minute. So from pre-cal, that's what you should have understood. Okay, or we have functions that are top-heavy. Okay, where the thing on top is greater than the power on the bottom. Okay, a top-heavy rational function has no horizontal asymptote. Okay, and what we will find is the limits of these ones that have no horizontal asymptote are either positive or negative infinity. Okay, so the limits of these rationals. Now the interesting one is when it is neutrally heavy. As in the numerator and the denominator both have the same power of x. Okay, like this. Notice that they are both x squared. And in our pre-calc class, hopefully you learned that if this was the case, you look at the coefficients of your first powers of x. Okay, hopefully you remember that. So in this case, we would have a horizontal asymptote at y equals 3. Because 3 divided by 1 is, of course, 3. Okay, now we're going to show why today in calculus that happens to be true. But those three things come from your pre-calculus class. That if it's bottom heavy, you have y equals 0 as a horizontal asymptote. If it's top heavy, there is no horizontal asymptote. And if it's neutral, then you look at your coefficients. So let's see if we can take those ideas and apply them here to some actual problems. So what is the limit for this function as x goes to infinity? Okay, so we want to identify the function. What type of a function is this? This is a negative, right? So a negative odd function. Okay, this is a negative odd function as x approaches infinity. So if we look at a sketch of the graph, all negative odd functions basically look like that. So as x goes to infinity, where is the graph headed?
Negative infinity.
Towards negative infinity. The graph is going down to the right because it is a negative odd function, and that's the end behavior as x approaches positive infinity. Okay, moving over. Here we have another function. So is this a even or odd, and is it positive or negative? Okay, so let's do some analysis. What is x times x? That's x squared. And how many x's are going to be in here? Okay, also an x squared. Right? So is this going to be a positive or negative even polynomial? That's the question. Okay? We have 4 minus x squared. So if I do 4 minus x times 4 minus x, do I get a positive x squared or a negative x squared? A positive x squared. So I have a positive x squared times positive x squared, which means it is a positive even function. And hopefully you remember that every positive even function has n behaviors that go to infinity. Okay? All positive even functions open up, right? They're very happy. They are amazingly positive. So no matter what the limit is, it always is going to be infinity. Okay, the limit as x approaches infinity or negative infinity of an even positive polynomial will be positive infinity. Okay, the graph goes up at the end behavior. So how about our last one? If we look at just using the pre-cal, we'll notice that this is a neutrally heavy function, right? We have an x in the top and an x in the bottom, so this is neutral. And whenever we have a neutrally heavy function, we look at the coefficients. So negative 2 over 1 means we have a limit of negative 2. So there is a horizontal asymptote at y equals -2 because this is a neutrally heavy rational function. So now that our pre-cal is out of the way, let's talk about why that is by using the calculus definition of these limits. So here we have this same rational function, okay, and hopefully you can see that this is a neutrally heavy because we have an x squared on top and an x squared on bottom. Okay, so what we want to do in our limit analysis is division. We want to change this from our normal rational into something that's really crazy looking. Okay, so that we can take the limit of each part of it individually. So what we want to do is divide by the largest power of x in your denominator. So in this case, that would be x squared is the largest power of x in the denominator. So algebraically, we're going to divide every single one of these terms by x squared. Okay, every term we divide by x squared. Okay. So this is our limit analysis to find the limit of this rational function as it goes to infinity. Okay, so we'll rewrite again, once again, the limit as x goes to infinity of our new augmented rational function. So 2x squared divided by x squared is just 2. 7x divided by x squared reduces to 7 over x. 6 divided by x squared is in fact 6 over x squared. And now in our denominator, x squared divided by x squared is 1. 5x divided by x squared is 5 over x. And 6 over x squared is just 6 over x squared. And now we need to think about the actual limits of each of these things as they go to infinity. Okay, so we're thinking about the limit for each of these as they go to infinity. What is the limit of a constant as x goes to infinity? Well, it's just that constant. Okay, what is the limit of 7 over x as x goes to infinity? Right, this is a rational function that is bottom heavy. So the limit of a rational function that's bottom heavy is always just 0.
It's not bottom heavy though, right?
So now we look at our third term. The limit as 6 over x squared goes to infinity. Okay, once again is a bottom heavy rational function. So its limit is also going to be 0. Okay, and we do a likewise thing on the bottom. The limit of a constant as x approaches infinity is just that constant. Okay, the limit of our rational function, 5 over x, once again is bottom heavy, so it goes to 0. And 6 over x squared also goes to 0. Okay, so this is why it works in pre-cal, because these other limits as x goes to infinity happen to be 0. Right, so then 2 plus 0 divided by 1 plus 0 has a limit of 2. Okay, and that's exactly what we found during pre-calculus. So when it asks you to find the limit, okay, it wants you to show that limit analysis. Okay, so it wants you to do two things. It wants you to show what do you get after you divide by the greatest power of your denominator. So in this case, we're going to divide every term by x, because that is the greatest power of x in your denominator. So we divide all these things by x. Everything top and bottom we divide by x. Okay, so that will give us the augmented limit of x, because x squared divided by x is x, plus 3 plus 2 over x, all divided by 1 minus 1 over x. So when you do your limit analysis, calculus wants to see this function right here. Okay, show them what you get once you divide by the greatest power in your denominator. Okay, and now calculus wants to see your analysis. So the limit of x as x goes to infinity is infinity plus, what's the limit of 3 as it goes to infinity? Well, that's just 3. And the limit of 2 over x as x goes to infinity is 0. Okay, that's what we do here is we want to make that 0. And on the bottom, the limit of 1 is 1 plus 0, right? 1 over x, or rather, sorry, not plus, but rather minus 1 minus 0. So that gives us infinity plus 3 divided by 1, which is infinity. Okay, so as the limits of this function, right, as it goes off to the right, the y values are going up to infinity.
So we're not.
So here's that same problem as above, but now we're going to negative infinity. Okay, so we're practicing that limit analysis. Calculus is going to ask you to show the limit analysis. Okay, so don't just say it equals 2. We know it does. Calculus wants to make sure that you know how to do the limit analysis. So the limit as x approaches negative infinity. We're going to divide all of our terms by, once again, by x squared. Okay, it's the greatest power in the denominator. So the top will be 2 plus 7 over x plus 6 over x squared again. And the bottom will be 1 plus 5 over x plus 6 over x squared. Okay, calculus wants to see your limit analysis. The AP people want to know that you know why it's 2 over 1. Okay, so now we can do this, right? The limit as x approaches negative infinity of a constant is just that constant. Okay, and the limit as x approaches 7 over x is 0. And the limit as x approaches negative infinity of this rational is also 0. Okay, and then 1 plus 0 plus 0. The limit of this function at negative infinity is still 2. Right, the horizontal asymptote, positive 2. So looking at our last example, right, we have an x on the bottom, so we're going to divide every term by just x and perform the limit analysis. So here we're plugging in a negative infinity for x, so you get negative infinity as the limit of this function as x approaches negative infinity. Okay, so 2 more examples just to make sure you got it. So why don't you go ahead and maybe pause the video, try these for yourself, and then come back and see. So here are the last 2 answers to each of these. Okay, so for this one, the limit is negative 2 over 3. And for the second one, the limit is infinity. Okay, so they want you to do the limit analysis when you take the limit of a rational function to negative infinity or positive infinity.